All right, guys, so what we're going to be talking about here is we're finally going to get to the point where we've been talking about, saying, okay, there's got to be an easier way to take the derivatives, an easier way to find the derivative so that we can use it in finding the slope of the tangent line. If you remember, what we talked about before is we said, okay, the way we use the limit, and this definition does always work. We can always use this formula to find the derivative of any function that we want. And it works every single time. And it's miraculous that it works every single time. We discovered that if we had something like x to the third, the derivative of that would be like 3x squared. Or we did maybe like x squared plus 2x, and we found that the derivative of that was 2x plus 1, using this limit definition of the f of x plus h minus f of x all over h. And that really did. Once we found that equation, remember, these right here, we could say that these are like f prime of x. Those are simply formulas that allow us to find the slope of the tangent line of any given x value of the function that we took the derivative of. The problem is this method that we use, and it works, doesn't seem effective when we start looking at things that are more difficult, like x to the third plus 3x squared, or even like x to the sixth minus 4x, or more difficult functions in general, like the sine of x or e to the x. All of those have derivatives, but using these rules that we have, especially when I got like x plus h to the sixth power, where I have to multiply it out 6 times, like FOIL it out 6 times, that it's possible, but it's not something that we really want to do if we can help it. And so what happened was Newton started noticing that there were patterns that were emerging as he was finding these different derivatives. And he said, hold on, wait a minute. I think that there are rules that we can adopt instead of using the limit definition of a derivative. Instead, we started saying there are different rules. And so those are the rules we're going to learn. Now, if you've had AP Physics already, you know this first rule. The first rule says that if we have x raised to some number power and I want to take the derivative of it. So if I had something like x to the fourth, before we would have had to multiply that out, do the limit as h approaches 0, go on and on and on. And we would have found that the derivative was this using this way simpler rule. The rule says this. You take the exponent that is currently written, that x is being raised to, or whatever letter is being raised to, and you move that number down in front of the x. Okay? So and then we put an x, we leave the variable the same. The hardest part of all of this is remembering that the new exponent on what x was when we're trying to find our derivative is always the number we had minus 1. Okay, so in this case, it would be 4x to the third. Now that might seem almost too easy because we're done with this problem. This is the power rule. The power rule just says if I want to find the derivative of a function, all I have to do if it's x being raised to a power is I take the power, I move it down in front of the x, and I subtract 1 from the power, and I'm finished. Literally 2 seconds instead of taking 5 minutes to multiply all that stuff out, and it would have given you the exact same thing as if we had x plus h to the fourth power minus x to the fourth all over h, and having that be the limit as h approaches 0. It's amazing, and it's not something we're going to go into right now a ton as to why it's so amazing, but the fact that that works every time is absolutely incredible, okay? And so that's what this screen is just kind of explaining what we just said right there. So again, if I wanted the derivative of x to the fourth, that would just be 4x to the third. We talked about that one already. If I wanted the derivative of x to the 16th, I would take the 16, put it in front of the x, and then subtract 1, so it'd be like 16x to the 15th. Really, really easy. If there's a number out in front, sometimes people say, well, wait, there's a number out in front, do I treat that differently? Basically what happens if there's a number out in front is when we bring the number down, because there's already a number there, we just multiply those numbers together. So 34 times 3 is 102x to the 33rd. So if there's a number there, we just multiply it. The problem's no more difficult, and we still don't have to apply that old limit definition. Instead, we just say, oh, I just multiply those two numbers together. The power rule, again, it's incredible that it works every single time and that I do not have to apply that long limit definition. Instead, I can just find the derivative in, honestly, 5 seconds tops of functions like these. A couple derivatives using the power rule that people get a little bit confused on are these two. So I want to talk about these real quick. If I wanted the derivative of 3x technically that is 3x to the first power. Now, if I were to apply the power rule, bring the 1 down and times it by the 3, so I would get 3. If I subtract 1 from that exponent, I would get 0, because 1 minus 1 is 0. So what we have to remember here is anything raised to the 0 power is 1. So what this is really saying is 3 times 1 is 3. Many people, when they look at the derivative of 3x, say, oh, the derivative is just 3. And that is correct, but they don't know why. So we just kind of walked through that right there. Another time that we can use the power rule is when we have something like this. You're going to find out in just a minute that when we're dividing things, it absolutely is the worst way to try and take a derivative, although we do have a formula for it. So in this case, I could rewrite this formula using rules of exponents that we talked about earlier this year, and I could say that that is x to the negative 2. Again, we just changed the exponent. Usually we change negative exponents to be positive. But if I wanted to, I could rewrite this by moving the x back up top and saying that the derivative, or excuse me, that the exponent is now negative. Well, the power rule works for negative exponents as well. So I could say that this is negative 2x, and this is where you have to be a little bit careful, because negative 2 minus 1 is actually negative 3. So my derivative of that one would be negative 2x to the negative 3. If you don't like negative exponents, you could say that it is negative 2 divided by x to the third, and that would be your derivative as well. So either way you want to write it is totally fine. So that is the power rule. Now the next rule we're going to talk about is a constant rule. Anytime you take the derivative of a constant number, whether it's 5 or 7 or 12, all of those graphs, if I were to graph all of them, although they're in different places, all of them look the same in that all of them are simply a flat line. Well, the slope of a flat line is 0, so remember the derivative tells us how we find the slope of a line, or of a tangent line, and all of these already are tangent lines, so the derivative of each of those, so if I were to take the derivative of any of those numbers, the derivative would always equal 0, of any of them. Anytime you have a constant number, the derivative is just 0. Okay? Another way you want to think about that, if that doesn't make sense, is technically a constant number is 5 multiplied by x to the 0 power. So what I could do is use my power rule again, bring the 0 down. 5 times 0 is 0, and then it doesn't matter what x is, even though it's x to the negative 1. 0 times anything is still 0, so you could look at it that way as well. Now you might be saying, okay, that's fine, but all we've looked at so far are like single terms. What happens when we have, we already talked about that, what happens when we have a function that has multiple terms? Well, again, the nicest thing about these derivative rules that we found is you can apply them to a term at a time. So the derivative here, I just have to ask, instead of saying what is the derivative, and I have to go x plus h to the third plus 3 times x plus h squared, on and on and on, we can just say, oh, I know the derivative of x to the third is 3x squared. I know the derivative of 3x squared is 6x. I know the derivative of negative 2x would just be negative 2, and then as we just discussed, the derivative of a constant number, the plus 1 would be 0, and I would get the derivative is just 3x squared plus 6x minus 2, and we'd be finished. So we don't have to apply anything specific, we just take the derivative one term at a time. And so that's really nice. Now again, if you've had AP Physics up until this point, you probably knew all of those things. But what we're going to talk about now is something that you might not be quite as well aware of. And that is what happens if we have two functions that are multiplying together, and I want to take the derivative of those two functions that are multiplying. What we do when we have two functions that are multiplying together is we use what is called the product rule. Now the product rule is just something that we use. The nice thing about the product rule when we use it on the AP test is you do not have to simplify down. And we'll talk about that when we look at an example here in just a second. But the derivative of two functions multiplying together is simply you write the first function down. That's what this part is saying. Then we multiply that by the derivative of whatever the second function that's being multiplied is. And you just identify your two different functions as f of x and g of x. Then we put a plus sign, and then we write down the second function, and we multiply that by the derivative of the first function. Okay? And in general, we use this if there's no easy way to multiply those two functions together to start. It's always easier if you can help it to like simplify it down a little bit before you take the derivative. But sometimes, like in this problem, that's not really practical. I don't want to multiply x squared to everything, and then 3x to everything, then 1 to everything, then combine like terms, and then take the derivative, especially since I can just use my product rule. My product rule says if this is f of x, and this is g of x, what the product rule says is, I write down my first function. So I just write down f of x, which in this case is x squared plus 3x minus 3x plus 1. Then I multiply that by the derivative of g of x, which in this case is 3x squared minus 10x minus 7. And hopefully you can see that that's what the derivative is. I did that a little more quickly than I have in the last couple of examples. So this, again, is f of x. What I have here is g prime of x. Plus the second function, we've identified that as g of x, so I've got x to the third minus 5x squared minus 7x plus 2. And we multiply that by the derivative of f of x, which is 2x minus 3. Now you might be saying, well, how did that help me at all? Because, yeah, that looks bad and I still have to multiply everything out. The way that that helps us is on the AP exam, they do not expect you to simplify this down. So that would be your final answer. We don't have to do anything else with that. We just leave our answer like that, and we're done with the problem. Notice there's way less algebra going on here. There's just calculus, and we leave our answer just like that. So that's how the product rule works. Product means we're multiplying two things together, in this case, functions. The quotient rule is a bit more complicated, but it's what we use when we have two different functions that are dividing each other that we cannot simplify. The derivative of one function divided by another function is the function that is on the bottom multiplied by the derivative of the function that's on the top minus the function that's on the top times the derivative of the function that's on the bottom, and then we divide that all by the function that is on the bottom squared. And I know that looks bad, and it is. Of all of the rules we learned, the quotient rule is probably the most difficult of all of them to apply successfully because it has so many parts, and they have to be written in this specific order. So let's take a look at this derivative. Okay, so I've got 3x squared minus 2x plus 1 divided by 2x plus 5. My top function is f of x. In this case, my bottom function is g of x, so we can use our formula. The formula says write down g of x, or what's on the bottom. So I go 2x plus 5. Then I multiply that by the derivative of what is on top. So I get 6x minus 2 there. Then, and this is important because a lot of people forget this, the quotient rule uses a minus sign. So I go minus the function that is written on top. That's f of x, so 3x squared minus 2x plus 1. Multiplied by the derivative of what is on the bottom. The derivative of 2x plus 5 is simply 2. And then we put that all over 2x plus 5, the whole thing squared. This is g of x, f prime of x, minus f of x, times g prime of x, all over g of x squared. So we just apply our formula again. The nice thing is you don't have to simplify down, and that is your answer. The last thing that we need to talk about here is this symbol, okay? D squared y over dx squared. I know it looks like there's squares in all sorts of weird places and we have to square things and that looks very complicated, but in reality, this is what is known as the second derivative. Sometimes you see it written as y double prime or f double prime of x, something like that. All this is saying is, I want to know what the derivative of the derivative that you just found was. So it's kind of like taking the derivative of the same function twice in a row. So if I had something like this, d squared y over dx squared of 6x to the fourth plus 2x plus minus 5, this is saying I want you to take the derivative. So I have my derivative here would be 24x to the third plus 2. Then it's saying I want you to take the derivative of what you just found. So the derivative of 24x to the third is 72x squared. The derivative of 2 is 0. So my second derivative in this case would be 72x squared. Second derivatives are very important, as we'll find out as we move forward and see applications for what is going on. But hopefully all of these rules make sense. Hopefully everything that we've talked about here makes sense and makes the derivative much, much easier to find. If you have any questions, please ask.